Here's an example of a stoichiometry problem that involves molecules. The heart of our stoichiometry problems is a mole-to-mole conversion, but we can also include other things like molecules or grams in our calculations. We've done mole-to-molecule conversions, and we've done mole-to-gram conversions, so we can add those onto our stoichiometry problems to make them a little more complicated and also sometimes a little more relevant to how we measure things in the lab. In this question, we're trying to find how many carbon dioxide molecules are produced when 0.750 moles of propane is combusted. We know the moles of propane, and based on our balanced equation, we can use stoichiometry to find moles of CO2. Once we have our moles of CO2, we can convert to molecules, which is what the problem is actually asking for. Our first conversion factor will be a stoichiometric factor, which uses our coefficients from our balanced chemical equation. Our second conversion factor will include Avogadro's number, because that's what we always use when we are converting between moles and molecules. Again, we'll start out with the number we're given in the problem, our known quantity of 0.750 moles of propane. We're going to go from moles of propane to moles of CO2. Moles of propane goes on the bottom of our conversion factor to cancel out. Moles of CO2 goes on the top since we're trying to find CO2. Our relationship from our balanced chemical equation is that 1 mole of propane will yield 3 moles of CO2. We fill 1 next to the moles of propane and 3 next to moles of carbon dioxide. We do 0.750 times 3, which tells us 2.25 moles of CO2 will be produced. Next, we need to convert from moles to molecules. We start with our 2.25 moles of CO2. We choose a conversion factor with moles of CO2 on the bottom to cancel out, and molecules of CO2 on the top, since that's what we are trying to solve for. We fill Avogadro's number next to molecules and 1 next to moles. We take our 2.25 moles of CO2, multiply by Avogadro's number, and that gives us 1.35 times 10 to the 24 molecules of CO2. Again, be careful with your units and your abbreviations. Do not abbreviate molecules as MOL because that's reserved for moles. Just write out the whole word, molecules. We can also do stoichiometry calculations involving grams. This is going to be very common because we can actually weigh out grams on the scale in the lab. The problem is that we can't do a direct gram-to-gram conversion between different substances. We can only go through moles using stoichiometry. So we'll have to get it into moles if it's not already. Then we do a mole-to-mole conversion, and then we could go from moles to grams if we need to. If we do need to convert from moles to grams or grams to moles, we'll use the molar mass. Depending on which way we're going, the molar mass could be either on top or the bottom of our conversion factor. Let's look at this example. We're trying to go from grams of magnesium hydroxide, which is actually one of the products, to grams of sodium hydroxide, which is one of the reactants. Again, it doesn't matter which side of the equation we're starting with or which side of the equation we're ending up with. We can go from any substance to any other substance as long as we do it through moles. First, we'll go from the 16 grams of magnesium hydroxide to moles of magnesium hydroxide using the molar mass of magnesium hydroxide. Then we'll go from moles of magnesium hydroxide to moles of sodium hydroxide using a stoichiometric factor. Last, we'll go from moles of sodium hydroxide to grams of sodium hydroxide using the molar mass of sodium hydroxide. First, we go from grams of magnesium hydroxide to moles of magnesium hydroxide. We have to get it into moles before we can do any sort of stoichiometric calculations. To get it into moles, we're going to divide by the molar mass of magnesium hydroxide. If it's not already given to you in the problem, you have to calculate it from the periodic table. We would have 1 times the mass of magnesium plus 2 times the mass of oxygen plus 2 times the mass of hydrogen, and add all those up and get 58.319 grams per mole. We're dividing by that number because grams is going on the bottom to cancel out. Remember, the molar mass always goes next to grams. When we do 16 divided by 58.319, we come out with 0.274 moles of magnesium hydroxide. Now that we have it in moles, we can do a mole-to-mole conversion to go from our product to our reactant using a stoichiometric factor. Since we're starting with moles of magnesium hydroxide is going to go on the bottom of our conversion factor. We're trying to find sodium hydroxide, so that's going to be on the top. In our balanced chemical equation, there's an understood 1 next to the magnesium hydroxide and a 2 next to the sodium hydroxide. So we fill those in as our coefficients in our stoichiometric factor. We multiply 0.274 times 2, and that tells us that we would need to use 0.549 moles of sodium hydroxide. The problem is that we can't actually weigh out moles in the lab. We need to weigh it out in grams. We're going to convert from moles to grams using the molar mass of sodium hydroxide. Sodium hydroxide has 1 sodium, 1 oxygen, and 1 hydrogen. We add those up and get 39.997. We start with our 0.549 moles of sodium hydroxide. Moles of sodium hydroxide goes on the bottom of the conversion factor to cancel out. Grams goes on the top of the conversion factor since we're trying to solve for grams. The molar mass of sodium hydroxide goes next to grams. We do 0.549 times 39.997 and come out with 22 grams of sodium hydroxide. We would weigh out 22 grams of sodium hydroxide and put it into the reaction to get the yield of magnesium hydroxide that was asked for in the problem. How many grams of ammonia are produced when 7.35 grams of hydrogen reacts completely with nitrogen to produce ammonia? 3H2 plus N2 makes 2NH3. Is the answer A, 82.6 grams, B, 41.4 grams, C, 1.56 grams, or D, 124 grams? The correct answer is B, 41.4 grams. In this problem, you're going from grams of hydrogen to moles of hydrogen using the molar mass of hydrogen, then moles of hydrogen to moles of ammonia using a stoichiometric factor which contains the coefficients from the balanced chemical equation. Then moles of ammonia to grams of ammonia using the molar mass of ammonia. Keep in mind that the hydrogen and nitrogen referenced in the problem are the diatomic molecules H2 and N2, so your molar masses will be the mass of 2 atoms added together. Here's a general flowchart of the types of problems that we could do related to stoichiometry. The heart of stoichiometry is in the center of this diagram, the mole-to-mole conversion using a stoichiometric factor. We can go from moles of A to moles of B or vice versa. As long as we can get 2 moles or from moles, we can do a variety of other calculations. We can find the number of particles, like molecules or atoms, using Avogadro's number to convert between moles and particles. We could use molarity to go between moles and volume of the solution. Remember, molarity is moles over liters. So if we know moles and we know molarity, we can find liters. If we know the molar mass of the substance, we can go between moles and grams. Once we have grams, if we also know density, we can find milliliters. Remember, density is typically in grams per milliliter. There are a variety of different calculations we can do related to stoichiometry. Really, we just need that heart of it, that mole-to-mole conversion. That's really all there is to stoichiometry. We're just adding on a few other calculations that we already know how to do.